Dear students, today we will be discussing about fundamentals of heat transfer, which is required for design of solar collectors. So, heat is a form of energy that can be transferred from one system to another as a result of temperature difference. The thermodynamic analysis is concerned with the amount of heat that is transferred as a system undergoes a process from one equilibrium state to another. The science that deals with the determination of the rate of such energy transfer is known as a heat transfer. The transfer of energy as heat is always from the higher temperature medium to the lower temperature medium, and heat transfer stops when the two mediums reach the same temperature. Okay? So, what are different modes of heat transfer? There are three categories of heat transfer: conduction, convection and radiation. So, we take help of Fourier law of heat conduction to understand the conductive heat transfer, and we take help of Newton's law of cooling to understand the convection or convective heat transfer. So, there are two categories of convective heat transfer. One is natural convection or free convection, and other one is forced convection. And when we are interested about radiation, so we must take help of Stephen-Boltzmann law. Okay? So, all the three modes of heat transfer require the existence of a temperature difference. So, if temperature difference is there, then only heat transfer will take place. So, now let us discuss about conduction. The conduction heat transfer is the transfer of heat between two bodies or two parts of the same body through molecular exchange, which are more or less stationary. Okay? The rate of heat conduction through a plane layer is proportional to the temperature difference. Okay? So, temperature difference. So, if we take these layers, okay, this one, and heat is transferring from T1 to T2 in this block. Okay? So, this temperature difference across the layer and the heat transfer area. So, this is the heat transfer area through which heat is conducted. So, but is inversely proportional to the thickness of the layer. Okay? So, that means this rate of heat transfer is proportional to area, okay, through which heat is conducted, then temperature difference between this layer. Okay? So, this interface is having a temperature 1 and this interface is having a temperature 2, and then there will be gradient because T1 is greater than T2. Okay? So, now as you understand, we are most interested about the rate of heat transfer. Okay? So, the rate of heat transfer Q is equal to Ka T1 minus T2 divided by del x. Okay? So, minus Ka del T by del x. Okay? If x tends to 0, we can modify this expression something like this. Okay? So, why this negative sign? Because heat always flows from high temperature to the lower temperature, right? And then this gradient is always negative. Because of that, we will have negative sign here. So, here K is the proportionality constant called thermal conductivity. Okay? So, what is thermal conductivity? Thermal conductivity is defined as the rate of heat transfer through a unit thickness of the material per unit area per unit temperature difference. Okay? This thermal conductivity of a material is a measure of the ability of the material to conduct heat. Okay? A high value of thermal conductivity indicates that the material is a good heat conductor, and a low value indicates that the material is a poor heat conductor or insulator. So, from here we can see at what condition we can say one material is insulator and one material is called conductor. Okay? And in more deeper sense, we can go back to the equations and we can see how these are related. So, this dt by dx is q by k, okay, by using this Fourier law of heat conduction. If we consider for a same q or same heat transfer, if k is low, then what will happen? This dt by dx will be large, and this is valid for insulators. Okay. So, that means large temperature difference across the wall will be there. Okay. So, if we take a wall here, so this temperature will be very high, okay, this large temperature difference. And for the same q, if k is high, then dt by dx will be small. So, if k is high, this will be small. Okay. So, this is valid for conductor, right. So, because of that, small temperature difference exists across the wall. Okay. So, this is very, very important, which can give an idea about the difference between conductor and insulator. And this table shows the comparison of different material conductivity. Okay. So, diamond will have 2300, silver 429, and mostly we will be using glass here, it is 0.78, and water you can see 0.607. Okay. So, that way you can see the comparison of thermal conductivity of different material. So, we need to select sometimes insulator, then what will be the conductivity of an insulator. So, that we must know, and accordingly we have to apply in our collector design. Okay. So, this figure shows the variation of thermal conductivity of various solid, liquid and gases with temperature. So, as temperature increases, as you can see some of the materials, say for example, water, it is first increases, then it is decreases, okay, with increase in temperature. And for example, silver, with increase in temperature, it is decreasing, right. And this table shows the comparison of thermal conductivity of two different materials, copper and aluminum. So, you see at different temperature how these values are changing. For example, if we consider copper at 100 Kelvin, so it is about 482, and if we operate the system at 800 Kelvin, you can see 366. Okay. So, for aluminum it is 302 at 100 Kelvin and 218 at 800 Kelvin. So, this variation need to be considered when we are dealing with high temperature application. So, one more term we need to define here is the thermal diffusivity, which is defined as heat conducted to the heat stored, and this is mathematically represented by K by rho Cp. So, Cp is specific heat and rho Cp is the heat capacity. Okay. You can see the difference in unit, joule per kg per degree Celsius, then joule per cubic meter per degree Celsius, and this thermal diffusivity is represented by meter square per second, which represents how fast the heat diffuse through a material, right. A material that has a high thermal conductivity or a low heat capacity will obviously have a large thermal diffusivity. As you can see from this expression, if we have high values of thermal conductivity and then this value is lower, okay, this rho Cp is the heat capacity, then we will have higher values of thermal diffusivity. So, the larger the thermal diffusivity, the faster the propagation of the heat into the medium, okay, that we must keep in mind. A small value of thermal diffusivity means that heat is mostly absorbed by the material and a small amount of heat is conducted further. Okay. So, this parameter is very, very important when selecting a material for thermal collectors. Suppose for example, for absorber or maybe the tubes through which heat transfer fluid flows. So, what will be thermal diffusivity? Once you know the conductivity and heat capacity, from that you can calculate what will be the thermal diffusivity. Okay. And this table shows the comparison of thermal diffusivities of material. Okay. So, silver you can see 147 into 10 to the power of minus 6 meter square per second. Okay. And copper and aluminum you can see 113 into 10 to the power minus 6, aluminum is 97.5 into 10 to the power of minus 6, and for glass it is 0.34 into 10 to the power minus 6. So, because glass we need to know what is the thermal diffusivity, and water you can see 0.14 into 10 to the power of minus 6. So, these values are required while designing solar collector. So, let us learn about convection or convective heat transfer. In case of convection, the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion, and it involves the combined effects of conduction and fluid motion. The faster the fluid motion, the greater the convection heat transfer. In the absence of any bulk fluid motion, the heat transfer between a solid surface and the adjacent fluid is by pure conduction. Okay? Let us learn three things here. So, this may be a wall, an isothermal condition, and we have fluid is at Tf, okay? Then Tw is greater than Tf, and these are fluids. What happens, since this temperature of this wall is more than this fluid, then due to this buoyant effect, this fluid will move along this wall, okay? So, this way it will move. And if we talk about force convection, what happens? We need to apply some kind of fan, and of course, no, this is a wall, it's dW, okay, and is Tf, and this fan will make the movement of the fluid, right? So, this becomes force convection, forced, and this is free, okay. This is due to the buoyancy effect, right? And if we, as we have learned, this Tw and this is a Tf, okay, and then fluid movement will be there, right. So, when the temperature difference produces a density difference which results in the mass movement, the process is called free or natural convection, okay. So, there is no active units are required to lift fluid from this ground state to the top of this plate, okay. So, when the mass movement of the fluid is caused by external devices like pump, compressor, blower or fan, the process is called force convection, okay. So, we need to apply some kind of active device to lift the fluid from the ground to the top states, okay. The heat transfer process that involves change of phase, okay, maybe solid to liquid, of a liquid are also considered to be convection because of the fluid motion induced during the process, such as the rise of vapor bubbles during the boiling or the fall of liquid droplets during the condensation, okay. So, what I have drawn here, this is the wall, and just immediate vicinity of this wall there will be a fluid layer, okay. This is the fluid layer. So, before convective heat transfer takes place, so there is a very thin layer exists when this temperature between this wall, temperature of the wall is more than Tf, okay. So, here pure conduction will take place, okay, then only convective heat transfer will exist, right. So, whether the convection process is natural or forced, there is always a liquid film immediately adjacent to the wall where the temperature varies from Tw to Tf. Heat is first conducted through this fluid film and then it is transported by fluid motion. So, this is something like this is the film, and maybe this film thickness is delta here, and this is Tw, and this is the Tf, okay. So, this will be something like this temperature gradient, and then only convective heat transfer will takes place, okay, and this is the pure conduction, okay. So, this rate of heat transfer, this Q will be something like this side. This rate of heat transfer through the film Q can be represented by this, Q is equal to minus Kf into A into Tf minus Tw to delta. Delta is nothing but the thickness of this film, okay, and this T, small t and capital T are same, okay, here. So, we can write small t also. So, Tf minus Tw is delta. Okay. So, this film coefficient of heat transfer or heat transfer coefficient H is nothing but Kf by delta. What is Kf? Kf is nothing but the thermal conductivity of this film. Okay. So, thermal conductivity of the film. Okay. So, we can represent now this will be something like this, Q is equal to H A Tw minus Tf, which is nothing but Newton's law of cooling. Okay. So, if heat transfer coefficient is more, means rate of heat transfer will be higher. Okay. The convection heat transfer coefficient is not a property of the fluid, that we must know. It is not a property of the fluid. It is an experimentally determined parameter whose value depends on all the variables influencing the convection heat transfer, such as the surface geometry, the nature of fluid motion, the properties of the fluid, the bulk fluid velocity. So, these parameters are dependent on this heat transfer coefficient H. Okay. So, there are many correlations to estimate the heat transfer coefficient. Okay. So, these are just a representative correlation. So, this correlation is Detach-Boltier correlations, which is valid for force convection. This Nusselt number is a function of Reynolds number and prandtl number. Okay. So, Nu is Nusselt number is equal to 0.023 multiplied by Reynolds number to the power of 0.8, then multiplied by prandtl number to the power of n. So, n is equal to 0.4 when the fluid is heated and n is equal to 0.3 when the fluid is cooled. Okay. And in case of natural convection, we can use this kind of correlation. Okay. These equations are developed based on purely experimental phenomenon. Okay. These values of V and A are flow specific, right. So, different conditions, these values will be different. We will learn in very deeper sense in the coming slides. So, at this moment we can solve a very small problem. Okay. So, this problem goes something like water flows inside a tube. Okay. So, water is flowing inside a tube. Okay. This tube diameter is 5 centimeter and the length is 3 meter and its velocity u infinity I can write is 0.8 meter per second. So, I am interested to calculate what is heat transfer coefficient and the rate of heat transfer, that is Q. Okay. And mean temperature is given as 50. So, mean temperature T mean is given as 50 degrees C. So, we need to find out the properties of the fluid at this temperature, and the wall is isothermal at 70 and wall is isothermal at 70. So, this is the 70 degrees C. Okay. So, fluid this is at 70 degrees C. Okay. So, this is not mean, this is actually no fluid temperature Tf is 50 degrees C. Okay. So, water temperature is at 50 degrees C. Okay. Now, what we need to do? We need to make the average temperature. So, what is the average temperature? T will be 70 plus 50 divided by 2, it will be 60 degrees C. Okay. So, this is the mean temperature at which we need to calculate the properties of the fluid, right. So, what are the properties of the fluid here? K value is given as 0.66 watt meter Kelvin and nu, that is kinematic viscosity, is given as 0.478 into 10 to the power of minus 6 meter square per second, and prandtl number is given as 2.98. We will study what is Prandtl number, what is the significance of Prandtl number in convective heat transfer in coming slides. So, we need to know the Reynolds number. So, how Reynolds number can be calculated? We already know U infinity I can write, then D, then we have nu. So, this U value is 0.8 and diameter is 5 centimeter. So, 5 into 10 to the power of minus 2 will give meter, and nu value is given as 0.478 into 10 to the power of minus 6. So, which is finally leads to a value to 3700. So, Reynolds number is found to be 83700, right, and Prandtl number already known to us. So, we can use this expression or correlation. So, as I said, that is Detach-Bolter equation, Detach and Bolter equation. So, this is something like Nusselt number is equal to 0.023, then we have Reynolds number to the power of 0.8, then we have Prandtl number is 0.4. So, condition what we have described before is applied here, and this Nusselt number is nothing but h d by k. H is the heat transfer coefficient, this is the diameter of the tube, and k is the thermal conductivity, and 0.023 Reynolds number already calculated 43700, then this is 0.8 and Prandtl number is 2.98 to the power of 0.4. So, if we substitute those values, and k value is known to us, it is 0.66, okay, and d is 5 into 10 to the power of minus 2. If we substitute, then finally we can calculate what is h. So, as per my calculation, it is 4075 watt meter square then Kelvin, right. So, h we have calculated now. So, once we know h, then our next calculation should be q, rate of heat transfer. So, what is the expression for rate of heat transfer? H A delta T, okay. So, this h value is 4.75, and what is the area here? So, it is a pi, and then we have diameter is 5 into 10 to the power of minus 2. What is L? L is 3, okay. This area is pi into d into L, okay. So, diameter we know 5 into 10 to the minus 2 and L is 3, and then delta T is how much? It is a 70 minus 50. So, it is 70 minus 50 is 20, okay. So, if we calculate it, then Q is found to be 38387 watt, okay. We can represent in kilowatt as well. So, this is 38.387 kilowatt, okay. So, Q will be 38.387 kilowatt, okay. So, in this problem what we have calculated is the heat transfer coefficient and rate of heat transfer when a fluid is flowing in a tube. If we maintain isothermal condition in the tube at 70 degree and fluid inlet temperature is 50, then we need to calculate or record the data at mean temperature, okay. So, how to calculate this mean temperature? Because this isothermal temperature is known to us, and plus 50 is the fluid temperature divided by 2 will give the mean temperature, okay. So, at that temperature we have to find out those properties. Then once we are done with that, then we need to calculate Reynolds number, and Prandtl number is given. So, we can use the appropriate correlation to estimate heat transfer coefficient, and once heat transfer coefficient is done, then we can calculate what will be the rate of heat transfer, okay. Now, let us learn the third mode of heat transfer, that is radiation or radiative heat transfer. So, unlike conduction and convection, the transfer of heat by radiation does not require the presence of an interventing medium. So, without any medium, this energy can transfer, okay. The heat transfer by radiation is fastest and it suffers no attenuation in vacuum. Okay? This is how the energy of the sun reaches the earth. Okay? This phenomenon has already been discussed in the initial lectures. The heat transfer studies were interested in thermal radiation, which is the form of radiation emitted by bodies because of their temperature. Okay? So, all bodies at a temperature above absolute 0 emits thermal radiation, that we must know. The radiation is a volumetric phenomenon, okay? And all the solids, liquids and gases emit, absorb or transmit radiation to varying degrees. Okay? So, always you will see all the objects radiates some form of radiation, okay, or some form of thermal radiation. So, if we consider Q is the total radiant energy incident upon the surface of a body, and some part of it will be absorbed, some part will be reflected. Okay? So, if we consider this, okay, this is a body and Q is the amount of energy may be falling here, some part will be absorbed, okay, some part will be reflected, some part will be transmitted. Okay. So, if we write this reflected is QR and this absorbed is QA and transmitted is QT, okay, then we can write Q is nothing but QA plus QR plus QT, and if we divide both the sides by Q, then what will happen? We will get this kind of expression, and what does it indicate? QA by Q is alpha, which is nothing but absorptivity, QR by Q is nothing but rho, which is reflectivity, QT by Q is transmissivity, which is represented by tau. So, alpha plus rho plus tau is equal to 1. So, for opaque bodies, this transmissivity will be 0 and alpha plus rho is 1. Okay? So, most solids are opaques. So, that we must know. A body which absorbs all the incident radiation is called a black body. A black body is also the best radiator. Okay? Most radiating surfaces are grey bodies, but no, this when we consider some kind of bodies, so these bodies are not always black body. It cannot absorb all the radiation what is falling on that body, right? So, most of the cases what we will encounter are grey bodies. Okay? So, it will have some emissivity. Okay? So, how to calculate this emissivity? This emissivity eta is nothing but actual radiation of grey body at T Kelvin to the radiation of black body at T Kelvin. Okay? It is a comparison. So, once we know this eta or say emissivity, then we can calculate the actual amount of radiation received by a grey body or emitted by a grey body. Okay? The rate at which energy is radiated by a black body at temperature T is given by Stephen-Boltzmann law. Okay? So, this Q is nothing but sigma A T to the power of 4. This sigma is nothing but Stephen-Boltzmann constant. Okay? Its value is 5.67 into 10 to the power of minus 8 watt meter square Kelvin to the power 4, and A is the surface area. Okay? So, for grey bodies we can write Q is equal to eta emissivity multiplied by sigma AS Ts to the power of 4. Okay? So, this emissivity is a measure of how closely a surface approximates the black body, for which emissivity is 1. Okay? So, for grey bodies emissivity will be in this range, okay, 0 to 1, right. So, now if I am interested to know the maximum amount of radiation that can be emitted by a black body, how we can calculate? Suppose for example, if we consider a black body which is at a temperature of 450 Kelvin, right. So, if we know this temperature, by using this Stephen-Boltzmann's law, we can calculate this maximum amount of radiation that can be emitted by the surface of this body. Okay? So, this is something like sigma T to the power of 4, because black body emissivity will be 1. Okay? So, that way we can calculate for this body which is at 450, it can emit maximum radiation of 2327 watt per meter square. Okay. So, that way we can calculate for gray bodies if we know the emissivities. So, this table shows the emissivities of some material at 300 Kelvin. You can see the aluminum foil, it has got 0.07, and we can say wood, it will have 0.82. Okay. So, that way we can compare the emissivities of different material, and we can select which one is best for our application. And if there are two gray bodies, and how these two gray bodies are exchanging heat through radiation. Okay. So, this can be calculated by using this expression Q1 to 2 is sigma A1, then this term is for view factor. Okay. So, T1 to the power of 4 minus T2 to the power of 4. Okay. So, if we consider a gray body at temperature T1 and other gray body is at a temperature of T2, then radiative exchange will be something like this. Okay. So, this V factor for gray body can be calculated by using this expression. So, what does it mean? The fraction of total radiant energy leaving gray surface 1 and reaching gray surface 2. Okay. So, that take care of this V factor. Okay. So, this is 1 by eta 1 is the emissivities for surface 1, and this is the emissivities for surface 2, the area 1 and area 2 for the surface 1 and 2, and this F12 is the configuration factor. Okay, of two similar black bodies, or the fraction of energy that leaves the black surface 1 and is incident on the black surface 2. Okay. So, this can also be calculated by using this reciprocity theorem, which is nothing but A1 F1 to 2, then A2 F2 to 1, means from surface 1 to 2, then from surface 2 to 1. Okay. How this radiation exchange will takes place. Okay. So, we can draw few cases, say for two infinite parallel gray plates. Okay. That means all the energy leaving the surface 1 strikes surface 2. Okay. So, if we take just a two parallel infinitely parallel plates. Okay. So, this condition is valid for design of flat plate collector. So, because maybe this part we can consider as glass cover and this part may be absorber. Okay. So, how this radiation exchange takes place. So, this knowledge we can apply for designing this flat plate collector. Okay. So, for this case A1 is equal to A2 and this configuration factor is same, and our view factor can be calculated by using this expression. Okay. So, this P factor is a function of two emissivities of the surface where exchange of radiation is taking place. Okay. And for concentric cylinders or spheres, if A1 is the surface area of the inner cylinder, then F12 is 1 and we can use the expression for V vector something like this. Okay. And when the enclosed body, say area A1 is very small compared to the enclosed surface. So, this is something like A1 is very small compared to this surface. So, under that condition this may be A2. So, this V factor is something like the emissivities of the internal one. Okay. So, that way we can calculate what will be the V factor. So, once we know this V factor, then we can use this expression for radiant heat exchange between two gray bodies at temperature T1 and T2. Okay. So, that way we can calculate the radiative heat exchange. Okay. So, area A1 is known, temperatures are known, and this constant is known to us, right. So, this knowledge will be required in designing a flat plate collector. Now, let us take one more exercise. Okay. So, this problem goes something like a long steel rod of 2 centimeter diameter. So, it is a 2 centimeter diameter is to be heated from 450 degrees C to 550 degrees C and it is placed concentrically in a long cylindrical furnace. So, this may be a cylindrical furnace, okay, and this rod is kept there inside the cylindrical furnace, and inside diameter of this cylindrical furnace is 16 centimeter. Okay. So, inner surface of the furnace is at 1100 degree C, and its emissivity is 0.85 here, and emissivity of this rod is 0.6. Okay. So, we need to calculate the average rate of heat absorption during the heating process. Okay. So, how to proceed it? So, we must know A1 by A2, because why this is required? We need to calculate this Q factor (1 to 2) is 1 by eta 1, then A1 by A2, then 1 by eta 2 minus 1. Okay. So, this A1 by A2 is required. So, here how to calculate A1 by A2? This area. So, no pi will cancel each other. So, finally, what we will have? We will have 2 by 16, 2 by pi dl. Okay. So, diameter is so this is 1 by 8. Okay. So, this area is nothing but pi dl. Okay. So, per unit length we need to consider, and again here this is small letter small d, this is capital D, this is L. Okay. So, that way you can calculate what is A1 by A2. So, A1 by A2 will be 1 by 8. Okay. And these values are given to us. Okay. So, once we substitute these values, 1 by eta 1 is 0.61, 0.6 plus A1 by A2 is 1 by 8, and then this is 0.85 minus 1. Okay. So, if we do the calculation, it will be about 0.592, right. So, this Q factor value is 0.592. Now, we need to calculate initial rate of heat absorption. Okay. So, if we are interested to calculate initial rate of heat absorption, by radiation, and we know the temperature initially it is 450, then I will write Qi is something like sigma A1 V factor 1 to 2, then we have T1 to the power of 4 minus T2 to the power of 4. Okay. This T1, if we consider this is at T1 and this may be at T2. Okay. So, for this case this T1 is 450. So, this has to be in Kelvin. Okay. So, 450 plus 273. Okay. So, it will be 723 Kelvin, right, and this T2 is 1100 plus 273, because radiation exchange will be initial this temperature to this furnace temperature. This furnace is already maintained at 1100 degree C. So, it will be 1373 Kelvin. Okay. So, if we substitute this value and sigma is known to us 5.67 Stephen Boltzmann constant into 10 to the power of minus 8 watt meter square Kelvin to the power 4, and area is pi, D's diameter is 2 centimeter, centimeter means that is meter will be minus 2, 10 to the minus 2, and this value already we have calculated, its value is 0.592. Okay. And T1 is 723 to the power of 4, then we have 1100 to the power of 4. So, this if we do these calculations, then we will get a value of something like 6908.72 watt per meter, okay, because it's a per unit, this length is not given, so that's why it is per unit. So this Qi is something like this, that is initial rate of heat absorption due to radiation exchange. Okay. So now we need to calculate the radiation or say rate of heat absorption at the end of the melting process. Okay. So this is the initial rate of heat absorption, at the end of the melting process, at the end of melting process. So same expression we can use, but only change will be the temperature. Okay. This final temperature here will be 550 plus 273. So this will be about 823 Kelvin. Okay. So if we substitute this value in this expression, so maybe I will write this QE, sigma value is known, then A1 is known and view factor value is known, only change will be 823 to the power of 4 minus 1100 to the power of 4. Okay. So once we substitute these values, then what will be the value of QE? It will be minus 6524.03 watt per meter. Okay. So QE we know now. So I hope you understand why negative sign is there, because no heat is received here. Okay. So emission is taking place from the surface and then heat is received by this rod. Okay. So we want average rate of heat absorption. So what will be the average rate of heat absorption? Average Q, if we write, then it will be Qi plus Qe divided by 2. So which is nothing but 6716.37 watt per meter. Okay. So average heat absorption during melting process will be 6716.37. Okay. No need to put this negative sign here, because this much of heat is absorbed, okay, in the melting process, right. So this is an example how to calculate rate of heat transfer between two bodies, and we also learn how to use this view factor, right. Now let us learn some of the non-dimensional numbers which are extensively used for heat transfer calculation in solar thermal systems. Okay. So this Reynolds number is the ratio of inertia force to the viscous force. Okay. So Vd, already we have used this Reynolds number in calculating Nusselt number, but we must know the importance of this Reynolds number. So it's inertia force to the viscous force. Okay. So if there are many force, then it becomes forces, so that's why it is forces. Okay. So we can write rho Vd by mu. Okay. And there is a critical Reynolds number, okay, at which the flow becomes turbulent. So we will have laminar flows, then turbulent flows, in between we have transition flows. So Reynolds number will give the information about this flow behavior. Okay. So this value of critical Reynolds number is different for different geometries and flow conditions. So if it is a pipe flow, then the value of this Reynolds number at which it will be turbulent will be different than in a flow over a flat plate. Okay. So as you can understand, this Reynolds number can be viewed as the ratio of inertia forces to the viscous forces acting on a fluid element. Okay. So this figure shows with increase in Reynolds number how this wax formation takes place. Okay. And Nusselt number is defined something like HL by K. Okay. So this Nusselt number represents the enhancement of heat transfer through a fluid layer as a result of convection relative to the conduction across the same fluid layer. Okay. The larger the Nusselt number, more effective the convection. Okay. A Nusselt number of 1 for a fluid layer represents the heat transfer across the layer by pure conduction. Okay. So, if we consider this two layer, this is at T1 and this is at T2, then temperature difference will be T1 minus T2. Okay. So, when this kind of situation arises, then we need to calculate heat transfer coefficient. So, in order to calculate heat transfer coefficient, we need to know this Nusselt number. Okay. Normally, in the convective studies, it is a common practice to make non-dimensionalize the governing equations and combine the variables which group together into dimensionless numbers in order to reduce the number of total variables. So, normally this is done when no numerical investigations of any complex flows are carried out. So, one more important parameter is prandtl number. Okay. The relative thickness of the velocity and thermal boundary layer is best described by the dimensionless parameter called prandtl number. Okay. This prandtl number can be defined like molecular diffusivity of momentum to the molecular diffusivity of heat. Okay. This is nu by alpha. So, the prandtl numbers of gases are about 1, which indicates that both momentum and heat dissipate through the fluid at about the same rate. Okay. If prandtl number is 1. Okay. Heat diffuses very quickly in liquid metals having prandtl number very less, and very slowly in oils where prandtl number is very large relative to the momentum. Okay. Consequently, the thermal boundary layer is much thicker for liquid metals and much thinner for oil relative to the velocity boundary layer. Okay. So, these are very important aspects when we are designing a very complicated system, or when we are designing flat plate collector. Okay. So, this table shows the variation of prandtl number for different material. For liquid metals, see the variation is very low, and in case of oils and glycerin, you can see it is a very huge number. Okay. So, this property or this number is very important as far as design of flat plate collector is concerned. And finally, we must know what is Nusselt number. Okay. So, Nusselt number is defined as the ratio between the bouncy force and viscous force. Okay. And mathematically, it can be represented by Nusselt number is equal to G beta dash delta T L cube by nu square. Okay. So, delta T is nothing but T s minus T infinity. So, if we have a plate is maintained at some temperature and free stream flow is at certain temperature. So, this net temperature difference you need to consider. Okay. So, this Nusselt number replaces the Reynolds number in the convection correlation equation. Okay. So, in free convection, buoyancy driven flow sometimes dominates the flow inertia. Therefore, the Nusselt number is a function of Nusselt number and prandtl number. Okay. So, this Nusselt number is a function of Nusselt number and prandtl number. Okay. And also we define release number, which is something like Nusselt number multiplied by prandtl number. Okay. So, in most of the cases we will use directly this release number for calculation of heat transfer coefficient. The most important use of the Rayleigh number is to characterize the laminar to turbulence transition of a free convection boundary layer flow. Okay. So, for example, when this number is greater than 10 to the power of 9, the vertical free convection boundary layer flow over a flat plate becomes turbulent. Okay. So, just an example. So, we will solve one problem to strengthen the understanding of this Nusselt number and heat transfer coefficient calculation. in case of natural convection heat transfer. So, this heat transfer coefficient between inclined parallel surfaces, if we are interested. So, there are many correlations developed by many of the researchers. Okay. So, most importantly these correlations are used for this case, okay, when we are targeting for calculation of heat transfer coefficient between two parallel plates. So, Buschberg et al. Developed these correlations. Okay. So, there are certain conditions. So, first we need to calculate R A cos beta. So, this will guide you which correlation to be used for calculation of heat transfer coefficient. Okay. So, this value first we need to find out, then we need to see where it will fit. Okay. If this value is in between these two values, then we will go for this correlation. If the value of R A cos beta is in between this, then we will go for this correlation. So, accordingly we will use the third correlation, and properties are to be evaluated at the arithmetic mean of the surface temperatures, okay, the way we have done in case of forced convection numerical exercise. So, if R A cos beta is less than 1708, then we will use Nusselt number is 1. So, this is one more correlations developed by Holland et al. So, he has also suggested some kind of range with beta. Okay. So, this beta is inclination. Okay. So, like this flat plate collector, some inclination is maintained. Okay. So, this inclination we have to consider. Okay. Based on this inclination, we can use this correlation. If its value is between 75 to 90, then we can go for this. Okay. So, there are other conditions we have to consider for selecting these correlations as well. So, let us take a small problem to strengthen the understanding of what we have discussed in the last two slides. So, we need to calculate the convective heat transfer coefficient between two parallel plates. So, maybe we have to draw these two parallel plates, and it is separated by 20 mm gap is there in between these two plates, and it is inclined at 40 degree. Okay. And upper plate is at 50 degree C, and this plate is at 30 degree C. Okay. So, as we have discussed that at mean air temperature of 40 degree C, the air properties are given like so. This 40 plus 273 will be 313 Kelvin, right. So, at this temperature, values of thermal conductivity, then kinematic viscosity and thermal diffusivities are given, right. So, once you know this, then we can use this equation, right. So, already we know how we have got this expression. Okay. So, Nusselt number is like beta z delta t L cube by nu square. Then we have Prandtl number is mu into Cp by k, right. So, if we multiply it, beta dash z delta t L cube by nu means mu by rho. So, it will be square. Okay. So, here mu Cp by k, okay. Then rho will go out, then this will be mu may cancel here. So, 1 mu will be there. So, 1 mu will be there, and this will go, then finally then 1 rho will be here, then 1 rho will be here. So, that way this mu by rho is again nu. Okay. So, beta dash z delta t L cube by nu, okay, and this rho Cp by k is k by rho Cp is, so this k by rho Cp is thermal diffusivity, right. So, this will come at the at this place. Okay. So, this will be something like RA, Reynolds number. Okay. So, that is how we can use this directly. Okay. So, if we substitute this value here, so beta dash, as we know this beta dash, so I will write here beta dash is something like 1 by T mean. Okay. So, T mean is 313, okay, 1 by 313, okay, this is temperature coefficient. Okay. So, we will substitute this value 9.81 and this is 313 and then temperature difference is 20, this is 20 and L is the this 20 mm. Okay. So, this value is 20, I can write 20 into 10 to the power of minus 3 because in mm, and then we have beta g delta T L cube, right. So, this may be L cube. Okay. And we have alpha is 2.40 into 10 to the power of minus 5 and nu is 1.7 into 10 to the power of minus 5, right. So, if we do the calculation, so it will be something like this 2, 3, yeah, correct. So, this RA will be 12290.92. Okay. Then what we will calculate RA cos of beta. Okay. So, this is 12290.92 and cos of beta is 40, okay, 40 degree. So, it will come to a value of 941.39. Okay. So, now we can check which correlation to be used 1415.39, then we can go back and see 1415. So, 1415. So, this is 94. What is the value of this? 9415. So, this 9415. So, we need to use this correlation, right. So, this correlation means this one. Okay. Nusselt number is equal to 0.229 RA cos of beta to the power 0.252. Okay. So, here we can use Nusselt number is equal to 0.229 then RA cos of beta 0.252. Okay. So, if we substitute this value, then what we will get is value is 2.297. Okay. So, as we know Nusselt number is H L or D by K is 2.297. Okay. From here we can calculate what is H. Okay. Which is nothing but 2.297 multiplied by K. What is the value of K? 0.0272 and then we will have L. What is the value of L here? Is 20 into or 10 to the power of minus 3. Okay. So, this is something like 3.14124 as per my calculation, 24 watt meter square Kelvin. Okay. So, this heat transfer coefficient is found to be 3.124 watt meter square Kelvin. Okay. So, this is a very simple numerical exercise to know how to calculate heat transfer coefficient by using correlation once we know the mean temperature. Okay. So, this is a very applied exercise. Knowledge of this can be applied for designing flat plate collector. So, let us summarize what we have discussed today. So, we have discussed different modes of heat transfer which include conduction, convection and radiation, and also we have studied non-dimensional numbers related to the heat transfer, then correlations to estimate heat transfer coefficient, and also we have solved some basic heat transfer problem to strengthen the understanding, okay, how to calculate heat transfer coefficient, how to calculate rate of heat transfer, okay, So, I hope that you enjoyed this lecture. Thank you very much for watching this video.